Okay, we'll start on question 5. Okay, so question 5 is a bag either contains, a bag contains either $1 or $5. So how much would you be willing to pay for this bag? Well, there are some other words after this, but basically what this question is trying to ask is what's the expected number of, what's the expected, how much money you are expected to get from the bag, right? So if I denote X as the money you get from the bag, then expectation of X, we can use for all X times probability that X equal to lowercase x. So there are only two cases. With a half chance, we will get $1, and also with a half chance, we'll get $5. So eventually, this gives us 3. So this is also the amount of money you're willing to pay for the bag, because your expected loss will be 0 in this case. Okay, for part B, I added $1 bill to the bag, and then it contains 2 bills. The bag is shaken. I drew out a random bill out of the bag, and it's a $1. How much money are you willing to pay for this bag now? So basically, saying what's the expected number of money in the amount of money in the bag now. So here you have $1 that you just put inside, and another thing you don't know what it is. So let's denote event A to be. You draw your first draw is $1, okay, and event B to be originally there is a $1 bill. Okay, CB, the event that originally there's a $5 bill in the bag. Okay, so the probability that B would happen given A, we'll use the Bayes rule, our old friend. Probability A given probability B intersect A. So probability of A actually depends on what's the original bill in the bag. So we'll split it into 2 different cases. First case is probability of A and B plus the second case, which is probability of A and C. So probability of A and B here, we know that if the original bag is 1 and you draw 1, this would actually be 1/2. 1/2 is the probability of B times 1. Times 1 is the probability of A given B. Because if both bills are $1, then it's with probability 1 you will get a $1 from the bag. Okay, so this is a half times 1. This is the same as the denominator, so it will be a half times 1. The probability of A intersects C, so the probability that originally there's a $5 bill and then you draw a 1 from it. So the probability that originally it's 5, it's a half. And given that originally you have a 5, the probability that you draw a $1 bill from it is a half, because now it has 1 and 5 inside, so the probability that you will get this 1 is a half. So this will give you 2/3. Same here. So probability of C given A is exactly 1 minus the probability of B given A. Because you either originally there's a $5 bill or originally there's $1 bill. So this will give you the probability of 1/3. Now the expectation of X. There are 2 cases. With 2/3 of chance, you will get 1. And with 1/3 of chance, you will get 5. So eventually, this is 7/3. So that's the expected number of amount that you will get from the bag. Okay. So for part C, your friend lies with probability 0.7, and your friend says it's a $5 bill. So how much are you willing to pay now? So how much are you going to get from the bag now? So let's denote F to be the event that friend says it's $5, and A, B, it's actually $5. B, the event that it's actually $1. Okay, so the probability of given S, it's actually a $5 bill, is probability of S over, dividing the probability of A intersect F. So same here, we're breaking this probability into two parts because it actually depends on two different cases, which is what originally is the dollar in the back. So probability of A intersect F plus the probability of B intersect F. And denominator is still A intersect F. So probability of A intersect F being that it's actually a $5 bill, which has the chance of a half, and your friend says it's $5. Your friends basically tell the truth this time. So the friend told truth with probability 0.3, right? And then here, this is the same, half times 0.3 plus, okay, so with a half chance, it's actually a 1, and your friend actually tells a lie this time because the friend says it's 5, so the friend tells a lie, it's 0.7, and then this gives us 0.3. So probability of B given F is 1 minus probability of A given F is 0.7 in this case. So the expected amount of the money you will get is, with 0.3 chance, you will get 5, and with 0.7 chance, you will get 1. So eventually this gives us 2.2. Okay, cool. So last one is a bound question. The company is selling these bags, and for $2 each, you decide to buy us 1 million? Yeah, sorry. 1 million of these bags and hoping to make a profit. So what's found an upper bound of the probability? The solution used the indicator variable X to denote the amount of bags out of the 1 million bags that has $1 in it. I will be doing this using another way. If we denote Y to be the random variable that denote the amount of money you get from this 10 to the power 6 bags. So Y is the amount of money you draw from the bags. In Y I didn't subtract the amount you pay, so it's just the money that you get from the bags. Okay, so expectation of Y is N times the expectation of YI. YI meaning that the amount of money you get in one of the bag. Here N is just equal to 10 to the power 6. Okay, expectation of YI, I think we calculate in part A, so it's actually N times 3, right, in part A. Okay, actually we don't even need to calculate the variance in this case, because we care about the probability that Y is smaller or equal to 2 to the power 2 times 10 to the power 6. This is the amount of money you pay for the bags, so if you get less or equal than this amount of money, you will not get any profit. So this is actually, we can rewrite this in the terms of probability of Y is smaller or equal to 1 plus, not plus actually, minus delta times mu. Okay, so the mu in this case is just 3n, which is 3 equal to 3 to the times 10 to the power 6. So delta, so 1 minus delta times mu is equal to, what's happening here? Okay, is equal to 2 to the power 10 to the power of 6. So we solve for mu is equal to 3 times 10 to the power of 6, and delta is equal to 1/3. So now we can plug in the plug in the Chernoff bound. 1 minus a third times 3 to the power of 6 is not equal to e negative 3 times 10 to the power of 6 times 1 over 3 squared over 2. So this will give us e to the power of actually 6 over 10 to the power. Okay, 10 to the power of 6 over 6. So this is the bound we get. Actually, I think this is slightly tighter than the bound they use when they use the amount of bags that have $1 bills inside it. So yeah, but this is also a way of using Chernoff bound in this problem.